Maybe we're looking for it. I don't know if I have a proof that's real. I'll look it up. If I do find, I'll throw it in there in the notes, okay? I'll throw it some mention of it on the Google Classroom stream. Okay. 9.3 updated, blah, blah, blah. Okay, questions? Those are pretty straightforward. No examples. Now what we're going to look at is different versions of this, different forms of this, and see if it diverges or converges. There's certain things that you can do. There's actually a lot of things you can do. There's a lot of things you can do. So, well, the first one we're going to look at is called the comparison of series. This is 9-4. We're going to look at the direct comparison test and then the limit of the comparison test. In other words, I'm going to compare what I don't know the limit of to something I do know the limit of. Now, we kind of already know that with the squeeze theorem. Remember that? The squeeze theorem says that if something's between two functions and it converges left and right, on top, above and below, then what's in between will also converge as well. Make sense? We already got something like that already in our quiver of possible ways to determine if something converges or diverges. But this is going to be a more specific value of that. Okay? So for convergence tests, the terms of a series have to be fairly simple, and the series must be special characteristics in order for the, in other words, we are limited to what we can do and cannot do. It's got to be a specific format, like for example, the P series. It's 1 over n to the P. That's it. There's no linear combination, there's no function of a certain degree. We can't do that with just the P series. But we can compare it to the P series to see if it converges or diverges. Let's say, for example, here's an example. This is a geometric series. See it? You multiply by 1/2 every time. You're starting with 1 and multiplying 1/2 every time. By the way, what's this converge to? Quick. Because the sequence converges to 0. What's the series converge to? Quick. A over 1 minus r. What's A in this particular case? What's the first term of the sequence? N is equal to 0. 1. Good. A is 1. What's r in this particular case? We will apply it to 1/2. Good. So it's 1 over 1 minus 1/2. What's that going to be? 2. Right. Cool. But notice, if I add an n, look what happens. It's no longer geometric anymore. But can you compare the two? Which one's always going to be greater? The first or second one? The second one will always be greater. So you can use the first one, which you know converges, to figure out the second one. Second one, P series. Boom. Does that converge or diverge? We just went over that. It converges because P is greater than 1. This is not. But can we compare the two? Which one is always going to be lower? The first one or second one? The first one, no. The second one will be lower because the denominator is greater. So if this sucker converges, what's underneath will also converge, right? Because it's bounding to what? What's the sequence going to here? What's the sequence going to? 0. What's it doing here? 0 as well, right? So it's always going to be positive, right? So it's bounded, monatomic, it's going to converge, right? So this one will also converge because it's bounded by this one. This one's greater than this one. So if you think about it, like the squeeze theorem, right? This one will always be greater. If it converges, what's below it will also converge. And they're both above 0. So yes, they're going to converge. Yeah,
So we could say that the second one,
yeah, because the second one's larger and it converges. The first one will converge too.
So, but for the first one, we can't say that because it's larger.
No, we can say that one because the p-value is a p-value. P series.
No, I mean for the first one.
Oh, this one here, up here.
Yeah.
Not necessarily. Yeah, it's a different method. But we can make a comparison.
We can't.
Okay, we know this one converges, so we can use that to determine this. What about this one? What is that? Can we figure out the series here? We can, remember there's three different ways to determine the series, right? One is pattern recognition. One is one of our tests. Well, the third one is to limits and limit to zero, in other words, integrate. Can we integrate that sucker?
Yes.
Yes. What is the derivative of n squared? 2n, there's n right there, just take the 2 out of there. It's a constant. Use U substitution, right? But this one not so much, but we can compare the two, right? Which one's always greater, the A or the B? The B is always greater, so we can make a comparison between the two. So that's what's called a direct comparison. We change our format to something we do know the convergence to. And make the comparisons between the two and say, if one converges, the other one should as well. If one diverges, the other one should as well. That's what direct comparison is all about. That's what comparison is all about. If you have a function greater than 0 but less than another function, if the other function converges, so is the one less than it. And here's the other one. Notice the reverse order. It's the contrapositive. If it doesn't converge, it diverges. So if the one here in the middle diverges, the one outside diverges as well. So this is a direct comparison test. One is kind of like a squeeze. If the one on the outside is greater, it converges, the one less than will also converge. And the contrapositive works as well. Remember, it's contrapositive, switch and negate. So switch and negate, switch the A's and B's and negate. The opposite of negation of converge is diverge. So if B diverges, if A diverges, B must diverge as well. So if the middle one diverges, the one on the outside must diverge as well. So this is different ways that we can compare. There's different ways that we can compare. Questions on the direct comparison test? Cool. Okay, move on. Moving on. So let's look at this example right here. What's that called, guys? Well, I take that back. It's not called that. Never mind. I was going to say it's a harmonic, but it's not. Why is it not a harmonic? That should be 3 times n, not 3 again. Sorry about that. So, guys, does that converge or diverge? What's it look like? 1 over 3 to the n, which is a what? Geometric series. And we know geometric series converge, right?
Yeah.
So which one would be larger? The 1 over 2 to 3 to the n or 1 over 3 to the n? Right, 1 over 3 to the n. So that would be like this one here, right? This would be 1 over 2 plus 3 to the n. This b, the n, would be 1 over 3 to the n. Notice the one on the outside, the larger one, converges. So what we can say about the lower one? It'll converge as well. So we compare that to 1 over 3 to the n, that's a geometric series. It's always going to be less than that because the denominator will always be greater. So by direct comparison, this sucker will converge as well. Question? So you take your function, you mold it, right, to something that you do know the converge diverges of. And then compare it, will always be greater or less. Then we can use the direct comparison test to make sure. This takes a little bit of talent. Because you got to see this right there in that entire function. That takes a little bit of talent. Your talent will come with it. You guys ready? Cool. By the way, I got an email from Ms. Hogan yesterday. She was so pleased with you guys. Yeah. She loved how you work on the board, working together. And she looked around the computers, they're all working on something. You weren't shopping. So thank you, I appreciate that. That made me look good. Yeah. I gotta look good. Because I'm ugly, so I gotta look good for something. Oh, no, no,
So
no.
you're just supposed to know
Come on, I said it was ugly. What are you saying is lost ugly?
that this is convergent.
I said it was ugly, so what's yours?
There
There we go, another A plus.
You're beautiful.
Now you want to.
Yeah, how is it integrated?
There's a line,
But
dude.
how come if it's n approaches infinity, shouldn't this be conversion? Because wait, no, because it's 1 over infinity, which is 0.
You got me going, stop.
Okay,
Questions?
I get it, ish.
All right, moving on. What do you think?
It's pretty awful.
What would you compare it to that you can't find? 5 over 3? Nice try. That's a constant. Thank you. Okay. Try the other side. You went to the
Is
right,
it?
go to the left.
Is it
5 over 2.
Close.
5
5 over 2 n squared.
I was right.
Okay.
Because what's
Oh my
5 over
God.
2 n squared?
Yeah, I don't know. Oh my gosh. Because
Nope.
no.
What's it called? What kind of series? B series. Very good. N is 2. Well, B is 2 n. So it's going to be 5 halves. Take that out. Just factor that. It's going to be 1 over n squared. 5 halves is a constant. Factor that out. It's going to be sum of n plus 1 to infinity of 1 over n squared. And P is 2. If P is 2, it converges, right? P is 2. P is 2. So it converges. So we got to compare. Now, which one will be greater? The 5 over 2 to the n squared, or this one, big sucker right here? Which will be greater? This will be less, right? Because the denominator is bigger. N is greater than 1, right? Right? So it's going to be always going to be increasing.
Wait,
Right?
I get it.
You're going to add 4n plus 3. That's always going to be positive, right? Like number 4 plus 3. 4 plus 3 is in a line. Y-intercept 3, slope is 4. That's like it's always been positive when n is greater than 1. So that denominator will always be bigger, which means the fraction will be smaller. So this will always be less than the P series. Since the P series converges, since that's greater, it's going to squeeze out the other one. It's always positive? Yeah, so it's positive. So it matches the condition here. It's always positive, and it's less than the P series. And the P series converges, right? Therefore, the sim must converge as well. Got it? So we pick something else. In this case, it's going to be 5 over 2 and 10 squared. And that's going to converge to the P series. And since it converges by the comparison, direct comparison test, this sucker will converge as well. What it converges to,
I don't really know
don't
what it has to do
but I
with it
do know
being
it
bigger or
converges.
smaller. Why does that matter?
Questions?
I don't know. Is it because
So pick something bigger or
because
smaller
of
that's similar to its
this,
structure
where is it? Because
and
A sub n
determine
is supposed
whether
to
or
be
not,
less
based
than
on the
or equal to
information,
B
it
sub
converges
n.
diverge. To diverge, you want something that you pick to be less than. And if you
Yeah.
tell that
A
diverges,
is
then
supposed
more
to
than
be
the
less
outside
than
diverges as well. That's the counterpositive direct comparison test. Questions?
I
Do it.
think.
Next one on your own. Oh, that's not on your own. Fudge. Let's do this one real quick.
Nuts.
This is not your own. Next one on your own. 1 over 2 plus square root of n. What's your P series right there? You see the P series? 1 over n. Which one is going to be greater all the time? 1 over 2 plus square root of n. Which one's going to be, oh wait, n is 1 or greater, right? It's always going to be increasing, right?
Is it always just gonna
So
be
2
increasing?
plus square root of n will always be increasing as well. So that's, but what's going to happen here? Oh, here. What's P in this particular case? 1 half. Crud. Yeah, that diverges. Crud. That's not going to help you. So we know on something less than that. Remember? Remember
P is less than one, it diverges.
formula says, if it
Wait, I knew that.
diverges, we want to see the middle one, some smaller diverges.
Oh, really?
If it's some smaller divergence, it's going to push the one on the outside out. So we want something less than that. So what they do is they want to say, okay, that's why I didn't give an example. We're going to write, instead of square root of n, put n there. That will always be less. Do you agree? And we know that's a P series with P equal what? 1. That will diverge. So if something less than diverges, something greater than will also diverge as well. It's always positive, always greater than 0, right? So it's not going the other way. So this one will diverge. Questions? So to prove something converges, find something greater than it. If something greater than it converges, you're good to go.
It's
We'll
less
do
than
this
this
problem.
value, it diverges.
You're trying to prove it diverges, find something less than that, and prove that that diverges.
No, I think it's if one of them
And you're
diverges,
good to go.
then
Questions?
the other one diverges.
On your own,
Which
go.
is why I don't
Oh,
understand why
crap,
you
I did
need
it again.
unless
I did it again. Oh, what happened to? That's the one I wanted you to do. I should have flipped them around. I'll do the next
Wait.
class, flip around.
maybe that's
Cool.
right.
All right, look at D
I
here.
just don't
Check it
understand
out.
it based on this.
This is 1 over 2 to the n minus 1. If I take out 1 over 2 to the
How do I know
n,
that this diverges?
that's a geometric series. It converges, but that's not what I want, right? I want the convergence to be on the outside, to
Like this
converge
is
inside,
cos
right?
P's.
I can't use the converse of that sign. Remember, only contrapositive works.
I forgot what a P series is.
So look back to your
Yeah,
theorem
yeah.
again. See it?
I really need to go back to 9.3.
That's my situation right there, right? My a sub n is 1 over 2 to the n plus 1. B, that's 2 over n. This sucker diverges. So you can't say this one's divergible. So you can't jump the gun a little bit. The direct comparison test does have limits. It does have limits. If the outside converges, so does the inside. If the inside diverges, so does the outside. It doesn't say anything about the outside diverging. Or worse, it says if something less converges, we don't know what's happening on the outside. If a sub n converges, we know nothing about b sub n. That kind of makes sense. That kind of makes sense. Yeah. If we know something about something less, we don't know what's going on. But we know if something going on less than is diverging, something greater will also be diverging as well. But if something inside or less is converging, we don't know what's happening at the greater than. So you have limits there. So D, you can't make the comparison there. It won't work. It's the wrong direction. You need something else to do. Questions? What could you use? Another test. Ready? Limit comparison test. That's the second thing in this section. Limit comparison test. The other one's direct comparison. We're directly comparing the value of a function to another value function. If we know the second function converges divergent, we know something, may know something about the second one. This one's a little different. This is the limit comparison test. The limit comparison test is based on the geometric series. It resembles the P series. It says the following. If we have a numerator function greater than 0 and the denominator function greater than 0, and the limit of the numerator divided by the denominator is a constant value, then both of these will either converge or diverge. Both of them will either converge or diverge. Which means if we know the convergence divergence of one, we can find the convergence divergence of the other as well.
So it diverges.
This is a little more flexible because it has to be greater than or less than. It's simply a ratio.
Yeah, because that's a.
We can get a ratio of two functions
But why?
to a
Is
limit.
it
We're good to go.
Why do we P series?
This is a ratio. We're talking about factors that are
So
common,
isn't it?
right?
So
When factors
wouldn't
are
you
common,
think
then
we
you
said
reduce.
that's
So if you take a
harmonic?
limit of
That's
something and
you
there's a
take
pesky
one
end there,
half of
so
one
a
over
power
n,
that's
is that
messing you up,
harmonic?
that doesn't convert to a limit,
Oh no.
you can divide by
Because
something
you
to get rid of it.
evaluate the one that you're given.
So it's a little more
One
powerful
over
in determining
n
convergence
to the
of
one
divergence
half.
of the series.
And since it's 1 over n to the 1 half, and that's
So
an
again, if I have
exponent,
two
because
functions,
P
both
is
greater than 0,
1/2.
works only for positive.
I think I get it. And if I don't,
Then
then I
the
just made
ratio
all
of
of
those
that up.
two, as n approaches infinity, if that value, that limit, that
Oh.
ratio is a specific value, some value n, L, then that says that both functions will either diverge or converge. If I know one, I know the other. If I know one, I
Okay,
know
so
the other.
that's
We're good?
a P series.
So let's take a look at an example here.
Yes? Yeah.
This is the harmonic series,
no,
right?
No. Okay, well, never
Will it
mind.
diverge or converge? Will it diverge or converge?
Let's just move on.
The general form of the harmonic series A n plus B. Will it converge or diverge? So I want to, sorry?
Diverge.
Let's find out. Let's compare it to something we do know. We do know that will diverge, right? So I take this, divide it by this, and see if that limit approaches a number, then both will diverge and converge, see? So I can compare that to this. What's wrong with the limit? As n goes to infinity, what's gonna happen about the denominator? It's gonna do what? It's gonna go to 0, right? So it's gonna mess things up. So you don't know if it diverges or converges. We don't, it doesn't conform to a standard form. But we know that 1 over n does. And to get rid of the n, we divide everything by n. Yay. We divide everything by n, I'm going to get 1 over a plus b over n. And when n goes to infinity, it's going to be 1 over a. So the ratio of these two functions, the limit of the ratio is equal to a value, whatever a is. So since this one diverges, what do we say about this one? It diverges as well. That's the limit comparison to the test. We want to manipulate this so we can easily find the limit. What do? We divide everything by n. So we divide by 1 over n, which we do know the status of. It's a harmonic series. That's p equal 1. That's sucker's going to diverge. Remember, p series will only converge if p is greater than 1, not equal to 1, or between 0 and 1. It makes no sense. A negative is oscillating at that point. So. Questions? So the answer to the question is the general harmonic series diverge. You'd be walking down the street and all of a sudden someone comes up to you and says, hey, general harmonic series, does it converge or diverge? You'll know. It diverges. Questions? But don't ask me that after I reply. You see me in the street.
Oh, because n is raised to the first power of p. But it's harmonic. So
This is
how
a
do you,
harmonic.
yeah, so
I'll
what's
do it.
that? But that, it doesn't say anything about harmonic.
We good? Questions?
Convergent or divergent harmonic series. It's not here. It's only about
That's
p
because the
series.
limit comparison
know?
test says that if the ratio of these functions
Oh, hold
approaches the
on.
limit, then
Go
they
all
both
the way
converge
down.
or diverge. We know this one diverges because p series of p equal 1. Therefore, this one must diverge as well.
Oh, P series, yeah.
Um,
P equals
P series 1. Remember, greater than 1 is that it converges. But between 1, negative 1.
Yeah, because if
between
p
0
is
and 1,
less than or
inclusive
equal
of
to
1, it
1.
will diverge.
But this is p series.
No, this
Oh,
is
but you can,
Question?
but you can apply the
That's
p
why we read
thing
that
to
in the class,
harmonic.
because we can do that.
Yeah, this is.
Oh, okay.
This
So
is
go
harmonic.
back.
Questions? We good? What you guys working
So
on?
then, we're
Um,
working on this.
Yeah, but
What can we
I'm just.
We're on 15. We're just trying to like work through it.
You okay with that? You have a question about it?
Could you give us like a second?
Sorry?
Could you give us a second?
1.
Okay. Like I think because
Oh,
n is
what the
raised
hell?
to the first power,
No,
then p is equal to 1.
All right.
Yeah,
Here are a couple of
Yeah,
examples. What was that
because
example?
P is
Same one we had
the
last time. Didn't
Yeah.
work, right?
but I
Didn't
just
work with
don't.
that comparison.
But why is it?
Will it
But
work
why
this
do you?
way?
Because it's
Let's
just-
compare it to.
Yeah, I know that.
1 over 2
So
to the
it's
n.
divergent.
What's going to
Like,
happen
all
to 1
two
over 2 to the n?
different
Will that
things, it's the same
converge?
thing. That's
Yeah.
dumb.
Yes.
Wait, so then. What's
So if the
all
limit
that?
of that
What is
ratio
that?
will
Now
converge to
that-
number, we're good to go. So
I
they
got it.
take that function, 1 over 2 to the n, which we know
Oh,
converges,
it's the
compared to what we
it's the
don't know,
a sub n
and
over
see if
b
the
sub
limit goes to
n.
1, and sure enough it goes to a value, and sure enough it does.
So then over.
So since it does converge, they both converge diverge,
Wait,
since the top one
Because
converges,
the
the bottom one was
theorem,
Yeah.
it's
converged
a
as
sub
well.
n over b sub n. So this is a sub n, and that's b sub n because a sub n is what you're given, b sub n
That's
is
a
what you
geometric
like
series.
compare to.
Okay, and why do we have to do that?
The
I
ratio
don't even
is
know, bro.
basically
Like, how do you
1/2.
even?
That's why 1/2 every time. 1 over 2 to the n. Questions? So we can prove that particular one converges, not with the direct
That
comparison.
kind of makes sense. You just have to know if
Use
it's convergent or divergent.
Goes over
Yeah.
what?
Doesn't matter.
I'm also just
Because
confused
the
as to why you
ratio
have to do
has to be a constant number,
Yeah.
right?
Yeah.
Yeah, what
Doesn't matter
exactly
what
are
that
we
ratio
finding?
is.
The limit?
I don't know.
Why are we
If you
comparing?
flip it, what's gonna happen?
So what are we concluding?
I don't know.
What's gonna happen? You get
I
2
don't
n
know
over
what
n
the
minus
point
1.
of this is.
2 n minus 1. You divide everything by 2n, what are you gonna get?
Babe, I don't
You're
know.
gonna get negative 1 over
of.
1, 2n. That's gonna be, 1 again, right? So that'll be
Oh, so you're
1
just using a
minus 2 over
different
n over 1.
method
It's 1 over
to
1 is 1.
evaluate the same thing.
Doesn't matter.
Oh, you're fine.
Hey, the
Yes,
ratio,
yes,
if
converges
a
or
function
diverges.
ratio converges, its ratio also
Wait.
converges well.
I'll ask.
Correction, if the
What
limit,
type of-
if the
what
limit
type of
of
function is that?
a ratio is a
What do you
number,
mean?
then the
Like
It's
B or
reciprocal.
actually
Armani?
geometric.
Oh, do we have to know that?
Unless it's 0.
I think
Ooh, that
so.
doesn't work that way.
Because the
Or-
rules.
I guess it
for,
wouldn't
like,
matter
if
if
it
your limit
converges
is
or
equal to
diverges
0.
are different.
But doesn't it have to be like finite and positive, and positive wouldn't be like 0?
Finite positive, you're absolutely right. There you go. That's where that, why it doesn't work with 0.
So if it's 0.
You're very observant, well done. He's saying it's gotta be finite positive. In other words, it's gotta be a specific value, and it has to be positive. In other words,
What
not
we're
infinite.
concluding is if what we're given
The
is
limit could be
convergent or
infinite.
divergent, that's it.
That's not the case here. That's positive. So in that particular case, if it's 0, it's not an issue, yeah. If it's 0 or negative, that's not an issue, that's very good. If it's 0, that's the issue. If it's 0, that's the issue. Cool. Very good, catch. Questions?
Mr. Shana.
Yeah.
So basically, all we're doing, like with these tests, is evaluating if what we're, like the function we're given is convergent or divergent. Like that's it.
Say that again? I didn't
So
hear.
through these tests that we're doing, all we're evaluating is if the function that we're given, like in the problem, is convergent or divergent.
Yes.
Okay, cool.
We're comparing it to one that is convergent or divergent.
Okay.
Now, we use direct comparison using kind of like a squeeze thing. Or we can do this limit test. And see
I
the
like this
ratio
one
of the
better.
functions, if that approaches some value, and that goes to infinity.
Okay.
If it does, they both converge and both diverge. If they both diverge, that means they're infinity, which means you can look, the Hospital's rule, get a limit. Yeah.
I hate
And
that
then
rule.
with the direct comparison
Yes.
test, the original has to be less than.
It has to be
The-
1 or 2. It's one of these two. If the larger one converges, the one in the middle converges too. Remember, it's always positive, so it's squeezing between 0 and the value above. We know the one above converges, so the one in the middle inside must converge as well. The other way around too is that if the middle one diverges, the one that's greater than it will diverge.
So like on slide 16, it says it won't. That doesn't work. Like the.
16 here.
Uh-huh.
There's no squeeze in this one, it's a limit test. You could use the,
It's business problems.
you could use the squeeze on this one, you could use the direct limit test
Here.
on this one, yes, you could. Well, no, you can't.
But like, why is that? Why won't that work?
You can't use another one, because you'd have to go, no, I would mess up, because you can't use direct,
Because
because
A sub
that
n
will
is
always
supposed
be
to be
less
less
than.
than B
Remember,
sub n.
it's the, if the middle one converges, we know nothing about the outside one. 2 to the n, 1 over 2 to the n would be less than, that would be A sub n in this case. If we know that converges, we know nothing about B sub n. That's not what the limit test says. It says that the outside one converges, the one in the middle converges. The contrapositive, that's also true. If the one in the middle diverges, the one on the outside must diverge as well. But if we know the one in the middle converges, we know nothing about the one on the outside. That makes sense?
Yeah.
Kind of.
Let's see.
Wait, how do you know?
Academic
Sub n.
season. Sorry.
That's okay.
A sub n and B sub n.
A sub n is what you're given. I'm pretty sure, because that's what it's been in our problems. I think that's what it is. So this is A sub n. So you see that A sub n has to be
So
lower
here is
than
your
B sub
B
n. So since
sub
it's
n
greater, you can't use this
function,
test.
right?
Because the theorem
The function, of
9.12
course,
says
is
that
value
A sub n
testing
has to be
then.
less than or equal to B sub n.
Not nice.
Yeah, I think that's it.
So the value
It's
increases, these are
overcomplicating it.
specific values, probably,
Girl.
or specific values, but the form looks like this, right? Okay, here's your A sub n. Always positive, right? Right? It's saying if B then converges and they're both positive, then the A underneath will be converging. And you'll notice that A sub n is always less than the B sub n. Got it?
Yeah.
Got it?
Mm-hmm.
It's also saying this one, the divergent. I need that one, I need this one, I don't need the one below, so. The other one says the other way around. It says if it's divergent, and again, so it used to put them there. If A sub n is divergent, In other words, the one below is divergent. Divergent, that's a sub n. That means the one above it will be divergent as well. Because it's pushing outward. Divergent means going up forever, and so is the a sub n. So that's what this one's saying right there. And again, the a sub n is less than.
To find if it's convergent, divergent, and see if it.
I have my colors right.
So like 1,
Yeah.
2,
So if it doesn't
Okay.
fall under the
So
theorem, you
that's
can't do
This is
it.
condition one,
but then that's greater
This is
than,
condition
so that
2.
doesn't work.
this is condition one
Yeah,
here,
since it's
right?
greater than, you can't use the theorem. This is why it says you can't do the test.
Okay. But
Okay.
the part D, the 1 over 2, the n minus 1, we take the minus 1 out, that becomes greater, okay? So just because this converges below less than, doesn't mean anything about the one greater,
Okay.
okay? If this one converges, if A converges, you don't know nothing about the black one here. One comparator could converge or diverge, we don't know. So direct comparison doesn't work that way, in case you're using that in this format. You good?
Mm-hmm.
Cool. Questions?
Together we are going to
Cool.
So I just have to make sure that this is
Here's another
less
one.
than this one.
N approaches 1 to infinity of the square root of n over n squared plus 1. N squared plus 1. Excuse me.
So that's A.
What can we rewrite this to make a comparison with? To get rid of the pesky one. Now guys, remember the derivative of n squared is n, right? We have square root of n, that doesn't work. Can't take the derivative, so what could we do to find the limit? What could we do to find the limit? Well, one way of doing it is comparing it to 1 over n squared plus 1. They're saying, wait a minute now. Well, it will approach it because it's roughly the same value. We know that a p-series, when it's greater than 1, will converge, right? So they can compare to that one. So they can try to get rid of the 1/2 by making it the derivative of that, which is what? N? So, some constant times n, right? So I have the square root of n, what I'd multiply to get n. N 3/2. So to change this to something I can find the limit of, I need to multiply by n 3/2. Which means dividing by 1 over n 3/2.
Girl, I know, right? This doesn't make any sense.
And 1 over 3 n 3/2 is a p-series that converges. So once we've done
Use the
this,
glasses call me quickly.
we can simplify this
N just disappear.
to this.
Or the 1.
And that
No.
is the limit I
Right
can
here.
find.
Well,
Otherwise, if I
usually,
squared, I get
it's
1
'cause it
over
always
1
goes
plus
by,
n.
like the
I
constant
had
or
to
whatever.
infinity is 1 over 1.
I don't know.
So it gets, that's where you get a little tricky. Trying to figure out a way to determine or find a,
Wait.
how do you change
Into
that
the 1/2.
to get a limit to approach the value? Then what you had to do to change it, can you find if it converges or diverges? Make sense? Make sense?
So that's what it's
So we
going
want to change this, okay,
Oh, it's because you always just get rid of
So
the
I can
constant,
find the
I'm
limit.
Sure.
and see if it converges to a specific number. If
I
it
think
does,
that kind of makes sense.
then we can say, well, the original function, when I change it, the ratio between those two will either both converge or diverge. So if I
Doing
change
the
it in some
limit
way,
comparison test,
so that I
why do
can
we
find
still have to
converge
compare
divergence,
these two?
the other one must do as well. So this one, I'm divide
No.
everything by, I multiply everything by n to 3/2 power.
Bro, I do not know.
which means divide by 1 over 3 times 2 power, and I can find a limit. This converges, right? That converges, right? So if that limit exists to a specific number, which it does,
Wait.
if this converges, this will move.
Didn't we just find the limit?
What?
The trick is to frame the
So
line.
you have
Is that the only
infinity
answer?
over
No.
infinity plus
There could
1.
be other
Why do
ways.
we have to do
How does that equal 1?
To get a
Okay, this I understand, but I thought we didn't
I
have to
could
compare them
multiply and
anymore
use,
if we're doing the
let's see.
limit comparison test. Like to compare
I
these
could
two.
multiply by 1 over n.
Well,
Because-
no, we
1/2.
didn't do the comparison
That
test
works.
because it didn't work. Right?
And the 1/2 is a series.
You're right.
P series.
That's
What divergent,
that's
right?
what like
Oh.
all of that
Well,
That's
give me
why
what I
you
want.
do. Okay, so here,
because that's just us
That'll give
finding
me
these
n
of it.
over n
Yeah.
squared plus 1.
So
But
if
take
you
the
have
L'Hopital's rule,
infinity
I
over
get- ooh,
infinity
that's
plus
not gonna
1. Oh, yeah,
That's not gonna work. I do
still don't
one.
understand that rule, dude.
Let's see,
It's
right.
been months.
So we want
Just
one
get
that's
the
greater
L
than
out
finite
L'Hopital's
or
rule.
positive. We want something
But you
that-
just
Is
take
that
the
it?
derivative.
Oh, I forgot.
Oh, 0, greater than 0, some specific value positive. Could we divide by, we could find anything else, could we? We could do anything else we could. How about n squared, would that work? Try n squared. Will that work? Yeah, 1 over n squared. Is that converted series?
How are we getting this?
That's a converted series. right?
Yeah.
That works. Matthew was making a comment. True.
And then
Let's see, I'll
those
say,
just cancel.
1 over n squared. We know it's converges, right?
Doesn't work.
I think you were saying something about the L'Hopital's rule. That's what
Let's
I was
try
talking
it.
about, but I don't.
Oh,
Try to limit.
okay. It's because
As n
take
approaches
the
infinity,
derivative.
Isn't it like derivative
square root of n over n squared plus 1, all over
don't
1
remember,
over
dude.
n
No, it's
squared.
just like literally the
I guess what I
derivative
want,
of the
what's
function.
that equal to? Limit.
Oh,
And
so
you
you
just
don't.
and you
approaches
just keep on
infinity of
taking
what?
it until
This'll
you're
be
able
what?
to take
That's
the
be
limit.
squared, that's squared, so sorry.
I don't want to do that.
That's gonna be what?
So,
That's
like-
the n to the what power? 5 halves?
If you keep
Over
on taking the
n squared
derivative,
plus 1, right?
at some point.
What do we define that limit?
Wait, what?
Is
We
he
just
doing
find that
that?
limit.
Why is he doing that? That's not going to
What
do
do you
this.
define that limit?
This makes a lot more sense.
L'Hopital, do it, what do you get? You get 5 halves into the, oh! I said n, wrote n. I hate when I do that, I do it all the time. 5 halves n to 3 halves power over 2n, right?
Mm-hmm.
Right? Is that, now plug in n to infinity, what do you get?
Okay, but like,
Infinity, so you do it again, right?
so like, yeah,
Oh,
so if you,
okay.
so if you take
So do it again, that's gonna be
that,
what?
that's gonna be,
15 over 4,
2n.
n to the 1/2 power,
and
all
then that's
over
gonna be,
2.
2.
Yay!
so then those are just gonna cancel out.
That doesn't work,
It's
does
just
it?
gonna equal
Why not?
1.
Oh, because 2
It's just gonna-
equals 1. That's so.
You gotta
It's
figure
gonna
out a way,
end up
yes, you
gonna,
gotta figure out
it's
a way
just
to
gonna end
make
up,
this
if you
so
keep on
that
taking
it
the
will be
derivative of
a
like
good number.
each thing, it's just gonna
And the
end
best
up
way to do
being
that is to get rid of that pesky square root.
Yeah, but what was he doing all
Yeah.
that?
Why do we have to do that? Like, what is the point of that?
What, by the way?
To find.
Ah, yes,
Because we
yes.
already know
Well,
that it
typical of-
converges.
Yeah, typical infinity 0. But again, because
Why do we have to take the limit?
that's the key, and that's the trick, and like I said,
What's
take a
the
little
Because
time.
we're finding L.
Take a little time and figure out what has to
But
be.
why?
I
Okay,
guess that's just what the theorem says.
questions? Time to go. 2 minutes, correct. It says,
Oh, we're making sure
hash
that
shift. How did, oh,
that L is finite
I
and
hate
positive to
that. I tried to
confirm
order flowers for my
that
wife
both converge.
That's kind of
on
weird.
Valentine's
I feel
Day,
like we're
which
confirming
is
5 different
tomorrow.
ways.
I know.
I actually spent extra money, so it will be tomorrow. When is it shipped?
Wait, what?
Today.
What's tomorrow?
And I spent 2 things. I got a goodie to share with her office, and of course,
Look.
flowers. The flowers are
Yeah,
coming
we
today,
actually
the
logged
goodies
in
are coming
today and did
Thursday.
some
I know, that's
stuff.
kind of crazy. It's our academic life.
You know what happens
Because
when
we've
it's
reached that
Thursday,
point of
right?
desperation.
You know what happens on these
We just have to
Thursdays,
teach
right?
ourselves. It's okay. Look, I should take notes.
What am I looking at?
And look, this is a fresh new notebook.
Ready?
Oh, I just realized that. I was like, wow, hers is 5 sections like mine. Like, and I didn't even consider, like,
People be so stupid.
She is fresh and new.
We good.
somewhat.
Objective for today was the direct comparison and the limit comparison test. Any questions? I don't think we got all the examples, but you can.
There's one more.
Yeah, there's one more.
I wonder what you do on your own.
Darn it, you didn't get to that one, okay. We have some good questions though.